So voltage division is when I have a voltage that's basically being applied across a bunch of series resistors, and I want to find the voltage drop across each individual resistor in the circuit. So for this circuit on the left, you can tell that Vn is being dropped across R1 and R2, and the two resistors are in parallel. And so I can tell that the same current is going through these two resistors. And all I did on the right was simplify this circuit to Vn and Req. Req just being the sum of these two resistors. And I want to solve for the voltage V1 and V2. And I'm going to do that first by writing Ohm's law across these two resistors. So for R1, V1 equals I times R1. And for the right side, Vn equals I times Req, because Vn is the voltage across this resistor since this node is at ground. And yeah, it doesn't really matter for this one. So since I is the same for these two equations, I'm going to solve for I. So V1 divided by R1 equals I. Vn divided by Req equals I. Since these two currents are the exact same, since it's just an equivalent resistance, I can set these two equal to each other. So V1 divided by R1 equals Vn divided by Req. So at the beginning of the video, I said I wanted to solve for V1 and V2. So I'm going to solve for V1 here. So V1 equals Vn divided by Req times R1. So this is your voltage division formula for this particular scenario. And I can actually do the same thing for V2. So I can repeat this process for V2. The right side is the exact same. So V2 equals I, same current, times R2. V2 divided by R2 equals I. Setting these two equal to each other gets V2 divided by R2 equals Vn divided by Req. So that means V2 equals Vn divided by Req times R2. So as you can tell, the difference between this one, this formula here, and the one for V1 is just the resistor that I was multiplying here. V1 was across R1, so I had an R1 here. V2 is across R2, so I had an R2 here. So I'm gonna write this formula, at least the formula for V1, in a way that's more intuitive for me. So I'm gonna say that V1 equals Vn divided by R1 divided by Req, which is just me rearranging the variables, which also equals Vn, or Vn times R1 divided by R1 plus R2. So the way I like to think about it is, if I wanted to find V1, what percentage of the total resistance is this resistor taking up? Because per Ohm's law, V equals IR, the larger the resistance, the larger the voltage drop, if you're keeping current constant. So in this case, I like to think about it as, so I have my resistor here, what percentage of the total resistance is that? And so this is just your simple percentage formula. R1 over R1 plus R2, you're just finding the ratio of like how much this R1 is in comparison to the sum. And so you can just rearrange this or rewrite this for V2. So V2 equals Vn. So this is your voltage that's being applied across both your resistors. And the percentage that R2 is taking is just R2 divided by R1 plus R2. So in this case, you're focusing on R2 rather than R1. And you're just calculating, okay, how much of the total resistance is R2? And that's just R2 over R1 plus R2. So in this part of the video, I'm just going to go over the conditions that have to be present for you to use voltage division. And so the main condition is that the resistors are in series and that your voltage is applied across all your resistors. So again, I'll just show that with an example, a quick diagram. So you have your voltage source here, and it's being applied to all these resistors. And I have my ground node here. So R1, R2, R3. So this voltage here, it's being applied across all three of these resistors. And I know the resistors are in series because the same current is flowing through each resistor. So those are the conditions that have to be present for you to use voltage division. Later in the video, I'm going to go over an example showing this more clearly. So the next thing I'm going to do is just generalize the voltage division formula that I wrote down earlier. So if I have a voltage here that's applied across a couple of resistors, R1, R2, and Rn, V1, V2, and Vn. So this voltage, as I stated earlier, is being applied across all of the resistors. And in this case, the voltage applied across all the resistors is just V, because you have V here and 0 volts here. So the voltage applied across all the resistors in total is just V minus 0, which is V. So what I want to find is Vn in this case. So I'm just generalizing it. So what you're going to do is you're going to take the voltage applied across all the resistors, which is V, and then you're going to find the percentage of the total resistance that your resistor takes up. So in this case, my resistor takes up Rn divided by R1 plus R2 plus ... R all the way up to Rn. So again, all I'm doing is I'm finding what's the total voltage applied across all the resistors, and then I'm finding what ratio does my resistor take up out of all the resistors. So this can be simplified to Vn equals V divided by Rn or V times Rn divided by Req, where Req is just the series resistance. So either of these formulas will work. I personally find the top one more intuitive because, again, I'm finding the voltage across all my resistors and the resistance that my resistor takes up out of all the resistance. So this is my resistance divided by all the resistors in series. So I'm going to go through an example to help you gain a little bit more intuition for voltage division. So the way I like to think about it is, just looking at this example before even solving anything, is that your resistor, in this case, is this middle one, 3 ohm resistor. Your resistor is consuming a certain percentage of the total voltage applied across all the resistors. So I'm going to write that down. Is consuming a certain percentage of voltage applied across all resistors. And obviously, those resistors have to be in series. So if you just think about it this way, if your resistor, if the value goes up, this percentage is increasing, and the voltage across that resistor is also increasing. It's consuming a higher voltage when in comparison to the other resistors that it's in series with. So I'm going to write this out by just solving for this voltage V. So the first step I'm going to do is just find the voltage applied across all resistors. The second thing I'm going to do is find percentage that my resistor takes up. And third and final step is use the intuition to solve for V. So I'm going to go through these steps one by one. You can always use this to find the voltage across any resistor using voltage division. So step one, find the voltage applied across all the resistors. So in this case, I'm going to look at where the resistor chain starts, and I'm going to look at where the resistor chain ends. In this case, you can see that there's a voltage source being applied here and here. So at the start of the resistor chain, I'm at a voltage of 20 volts. At the end of the resistor chain, I'm at a voltage of 10 volts. So that means that I'm going to say Vin is just this voltage minus this voltage. That's the voltage across all the resistors. So it's just 20 volts minus 10 volts, which is 10 volts. The next thing I'm going to do is find the percentage that my resistor takes up out of the whole chain. And so in order to do that, I'm going to say, okay, so my resistor takes up, I'm just going to find that percentage. So which would be 3 ohms divided by 2 ohms plus 3 ohms plus 5 ohms. Because this is my resistor, and the total resistance is just that. So the percentage is my resistor over the total resistance, which is equal to 3 ohms divided by 10 ohms. So that's my percentage. It's taking up 30% of the total resistance. The last thing I'm going to do is use the intuition to solve for V, which is the voltage I want. And like I said, V is just the part of the voltage applied that your resistor is consuming. And that V is going to increase and decrease based on how big this resistor is. Because if that resistor goes up, this percentage is going up. And so I'm just going to use that intuition to solve for V. So I'm going to say V equals, I'm going to start with my voltage applied, which is V in, and I'm going to multiply that by the total percentage that my resistor is taking up, which is just 3 ohms divided by 10 ohms. So if I simplify this, I get 10 volts divided by 3 ohms times 3 ohms divided by 10 ohms. And since the ohms cancel out here, I get that my V is just 3 volts. So this is all that's saying is that this resistor is taking up a 3 volt voltage drop. So this voltage across here is just 3 volts. And so as you can see, if you increase the percentage that this takes up out of the total resistance, this voltage drop is going to increase. I like to think about it like it's consuming more of the voltage that's applied across the entire resistor chain. And so you can also do this just using the voltage division formula. I can show you how to do that. So I'm just going to say that V equals, again, the voltage that's applied across all your resistors. So 20 volts minus 10 volts. And then that's going to be over your resistor, so 3 ohms, divided by Req. So Req is just 2 ohms plus 3 ohms plus 5 ohms. So Req is just 10 ohms. Req is just 10 ohms, which gives you the exact same result as before, that V equals 3 volts. So the next thing I'm going to do is cover a more difficult example of voltage division. So this is a little bit more complicated example of voltage division. And even though I stated before that all the resistors have to be in series, I'm going to show you how you can easily use voltage division to find this voltage V1 that's across these two 8 ohm resistors. And so one of the first things I'm going to do actually is label the voltages at my nodes that I know. So as I can tell, as I can see, the ground node is down here, meaning that this node is at a voltage of 10 volts. And I can also see that this 20 volts is being applied across here. So this voltage is also at 20 volts. And so the first thing I notice is that the voltage across my resistor chain, I'm going to simplify this in a second, but the voltage across my resistor chain is 10 volts again. So as I said, step 1 was finding your voltage across your resistor chain. And so that's going to be, I'm going to say that's Vn again, equals 20 volts minus 10 volts equals 10 volts. Now, the second thing I told you to do was find out how much of the total resistance that your resistor was taking up. So the second step was just percentage of total resistance. But one thing that you can see here is that you actually have two resistors in parallel rather than a bunch of resistors in series. But one thing that you can easily do here is simplify these two 8 ohm resistors into one resistor that's an equivalent resistance. And as we know, if you have a bunch of resistors in parallel and you simplify that to an equivalent resistor, the voltage across the nodes in both of these scenarios will be the exact same. So this voltage V is the same through each one of these scenarios because that's the definition of parallel resistors. So all that means is that if I simplify these two resistors to one resistor that's an equivalent resistance, it's going to have the same V1 across it. And so the first thing I'm going to do is simplify these two resistors. So I'm going to call that R2. R2 is just going to be equal to, like I said, 1 over 8 ohms plus 1 over 8 ohms inverse. And so 1 over 8 plus 1 over 8 is just 1 over 4 ohms. Taking the inverse gets you an R2 of 4 ohms. So if you follow this process, you can simplify these two resistors into one resistor that's the equivalent resistance of these. So I'm just going to redraw that circuit, but I'm going to replace these two resistors with R2. And if I replace that resistor like I'm showing you here, it's going to have the same V1 applied across it. So I'll redraw that now. So V1 is still just the voltage across that resistor. And so the next thing I'm going to do is just keep going through my process. So I already found the voltage applied across the voltage chain, which is 20 minus 10. It's 10 volts. The next thing I'm going to do is find the percentage of the total resistance that my resistor takes up. So that percentage is approximately, or it's just 4 ohms divided by 6 ohms plus 4 ohms. So this is the percentage that my resistor takes up out of the total resistance in the chain. And so the last thing I'm going to do is apply my intuition. And my intuition just tells me that this voltage is going to be proportional to the percentage that this resistor takes up out of the total resistance. And so applying that formula is going to yield this. So V1 is just equal to total voltage applied, so 10 volts, times my percentage. So 4 ohms divided by 4 ohms plus 6 ohms. So 4 plus 6 is 10. So this is going to go to, it's going to simplify to this, meaning that V1, if you just cancel out the ohms and also cancel out the 10, it's just going to be equal to 4 volts. And so even though I had two resistors in parallel, since I was able to simplify them to one resistor that had the same voltage across it, I could find the percentage that that resistor takes up out of the total resistance, multiply that by the voltage applied, and I get the V1 that I wanted, which is the voltage across that parallel combination, which is the same as the V1 here.